Hello, and welcome back to our 12-part series on remote procedure calls, RPCs, for Web3 developers. This is a very in-depth series about what RPC is, what RPC calls are, how to do it correctly, why it's not trivial to do, far from trivial to do, and how you think about it correctly. So in the last two episodes, we covered the history in episode 1 to get a kind of like an overview of what RPC is and where does it come from and when does it come from. And then in the last episode, we actually built an RPC server, very simple, a JSON-RPC server. So you have actually experience actually building it. So it's not just theory. We're going to do a lot of practice as well. So we've come pretty far already. But now we actually just want to take not a step back, but just a step back from the practical, I suppose, and just kind of gain some more understanding of exactly what we built and what else is available, in the sense of, there are many different ways two computers can talk to each other. So today what we're going to cover is the many different ways we can make the same call, and we're going to get to essentially many things, but one of the core things in this episode is kind of like, why JSON-RPC? Why was that format chosen? And so we'll answer that. But it doesn't mean only JSON-RPC is used or can be used. We're in fact going to see it's not about picking one over the other, okay, in general, right? All right, so let's jump in to episode 3. So last time, right, we looked at this kind of call, JSON-RPC call, right? And we actually built this last time, right? We, again, no blockchain last time, but we had other methods like add and then some parameters 1 and 2, but same thing. It just calls some function on the server, and that server runs the function. We will get to the blockchain stuff later, don't worry. But anyway, this is what we did last time, right? This is just one way to ask a remote machine for something, all right? Here, I've actually listed 3 more ways you can do it. So one is called REST. You might be familiar with that. Maybe you aren't, doesn't matter, but this is called REST. So it takes a URL and an HTTP verb, right? So like you have your verb against that. This sort of noun and verb. We'll get more into that. Then this one's gRPC, this one here, the third one. And so what this is a function that's defined in a schema file. Okay, so you can almost think about it as you strictly defined a schema around exactly how it should behave, and you then compile that into some code instead of just running it. And then the last one here is a WebSocket subscription. All right, but notice that it has the same JSON-RPC envelope, if you will, right, as the original JSON-RPC call. But the difference between a normal JSON-RPC call and a WebSocket version of it, again, it's not one or the other. WebSocket is just, and we'll cover this in a second, WebSocket is more like how you communicate between the machines in terms of the underlying like transportation, okay? So this is just a connection. The WebSocket is a connection that stays open and pushes data back to you. So that's what a WebSocket does. For example, in a wallet, if you open MetaMask in a wallet or some other wallet provider, and you swap tokens or send tokens, you will definitely have a WebSocket connection open to your RPC provider, because they need to instantly update your balance as soon as you swapped or sent the funds, instead of kind of like polling, which can be very sort of, it can be slow first of all, and also kind of like heavy. So we'll see that a little bit later. But the idea here is just to show you that there are many different ways we can call a function on another machine, and we already touched on that in episode 1 as well. So that's the idea so far. Now, first of all, why are there 4, right? That's a question we'll get to. Why are there 4, right? If they all do the same job, why didn't we just agree on 1? We're going to try to answer that in this episode. The other question we're going to look at is, are they even competing, or does each one quietly win, right, somewhere where the other lose? And I've kind of alluded to that already, so you know the answer. But we'll see why that is, right? And we'll kind of dive into why. So that's going to be exciting. If you've always wondered, like, what is gRPC exactly? What is WebSocket exactly? What does it do in this context of RPC? Well, this is the episode for you. The third question we're going to ask, that probably matters for most of us, is why did blockchain, right, pick the first one, the JSON-RPC, the one we actually built last time? Why did they pick it? The simplest, oldest feeling of the bunch, if you will. We can also ask, what did that choice cost us, right? since we did it. So anyway, so at the end of this episode, you'll read all these 4 fluently. That's my goal. And you'll know exactly when to reach for each. So, you'll say, gRPC is perfect for this and so on, right? So you're going to understand the trade-offs baked in to every dApp that you've used. And yeah, I hope that's going to be, very exciting. So, first of all, I think to start, we should first of all look at a common confusion. It's kind of a confusion, I would say, that makes the whole topic pretty murky in general. So, you might have heard people, and people in general, they will say REST versus gRPC, for example. If you haven't heard it, that's fine, but some people might say that. And you might think, okay, REST versus gRPC, right? It might be like Ford versus Toyota. Like they're the same kind of thing, but they're actually not, all right? That's like comparing a sedan car to diesel to a highway. Right? None of that makes sense. They're not comparable. They're different things, right? So they're just answers to different questions, if you will. So that's how this works. That's one thing. Every RPC style, right, it's a bundle of 3 independent choices. That's going to become important. So it's 3 different axes, and they are different, okay? And that's how one might win on one axis, but not be so great on another axis, and so on. So we have 3 of these axes. So that's important to understand, okay? So it's important to understand these 3 axes, and once you see the 3 axes, it's going to be clear, why, they're all different and why they're all here. So let's do some grounding first. So in the last episode, when we actually built an RPC server, you remember we used fetch as our method. Every piece of that line we wrote, right, has a choice of one of the 3 axes when we wrote that line last time, okay? So basically, and we can scroll down to here, we can see that here. So these are the 3 axes, okay? So last episode we wrote fetch, and we wrote all the content of this. If you haven't watched it, please watch. It'll make more sense what I'm saying now. So what are the 3 axes, right? It all comes down to where you're sending it and how the bytes travel. That's one axis. That's sort of the interface model down here, you see? So that's the interface model. So again, that's sort of like where you're sending it, how the bytes travel. Where you're sending it and how it travels, that's the transport. Okay? So, where you're sending it and how do the bytes travel, that's transport. That's one of the axes. Then, what you put in the body and how it's encoded, that's the wire format. Okay, so that's another decision you have to make. So that's another axis. And then finally, right, whether you think of it as like calling a method or acting on a URL, there's a difference in sort of the mentality around what you're doing, and that's the interface. Okay, so that's the 3rd axis. Okay, so 1, 2, 3. So great. So axis 1 is, let's show it here. All right. So great. So axis 1 is an RPC action, which is a verb, versus REST, a resource, a URL. Okay, so this interface model is the mental shape of your API. So there are 2 big families. Now let's look at the 3 different axes in this table here. So basically what we have here is the interface model, and for the interface model, this is sort of like whether you look at RPC action, which is a verb, or a REST resource, which is, a noun. So that's what this means, right? So in REST, you're operating on a noun, on a user, and so on, right? So that these are nouns you're operating on a car, things like that. And in RPC, it's more verbs. So that's the interface model. The other model is the encoding that we do. So we can choose to encode it, and again, this is sort of the wire format, right? Like how is it encoded, is not encoded. So the encoding itself with JSON-RPC is text, right? And so the benefit of it being text is that you can read it, so it's easier to debug, to understand what's going on. And for gRPC, it's actually binary, so it's something called protobuf. Okay, there's also message pack, CBOR. This is not human readable, right? It's basically a row of bytes that we're sending along, smaller, faster, but you do need some tool to decode it, right? You can't just eyeball what it is. So that's the downside of it, right? So this axis is almost entirely independent of the first. So how you encode it, if it's text, if it's binary, doesn't really depend on whether you use, RPC or, REST or whatever you do. You can do RPC with text or binary. You can do RPC with both, okay? We're actually going to go much deeper on the binary formats in episode 9. So if you don't, don't worry, we're going to cover exactly how binary looks and what it does later, okay? But today, just think of text versus binary, and roughly what each costs. So there's a difference, right? When you send text, you're typically much more verbose versus binary. It's more compact and doesn't take up so much bandwidth. So that's sort of the point in general here. So transport as well, we're going to look at, right? So this is, you can think of transport as like the pipe, right, between the computers that the bytes travel through. That's what transport is. So we're looking at this column here, right? And from episode 2, we know HTTP, that's what we use there, right? So the request goes up, the response comes down, right? Goes up to the server, comes down to us, done. That's what we did there. That was HTTP, what's called 1.1. So you see it like HTTP/1.1. But there's also HTTP/2. This, with HTTP2, for example here, that's what gRPC uses, you allow a lot more requests to share one connection at once. Many requests, right? And, then there's also WebSocket in terms of transport. That's the final thing. So the WebSocket is like a connection you make that just stays open. So either side can send a message at any time. So it's not like, hey, I want to talk to you. Here's something. And then it sends it back. Oh, hey, I want to talk to you again. It's like, and those are all separate connections. No, WebSocket just like creates the connection, keeps it alive, and they can just keep talking back and forth. All right? That's why it's very efficient for like real-time streaming. I know, when I send a transaction and I need to update the balance, I'm going to set up a WebSocket to listen for that update because I know it's coming soon. And then, a few hundred milliseconds later, balance updated, and I can close the connection again. But I was listening to it so that I could get it as fast as possible. All right? That's an example of WebSocket. So, okay. So basically each of these, right, JSON-RPC, gRPC, REST, and technically WebSocket, but not really. And you'll see from the table why, but we'll cover it in a second. But it's basically like a bundle of these, right? So when we say JSON-RPC, we're talking about a particular interface model, an encoding and a transport. Okay? So those are the three axes. That's what we mean by that. If we say gRPC, we're also talking about another sets of 3. Okay? So that's what it means. So think about it like in terms of that. All right. Now, notice one thing. REST is kind of the odd one out here. I mean, WebSocket is too. We'll get to that. But REST is an odd one out of the first 3 because basically it's the only one that changes the interface model. Okay. So, that's why it's often asked, I guess, like people ask the question, is REST actually RPC, right? Because it doesn't, you can kind of see it doesn't really, like, it actually changes the actual interface. Okay, so people are saying, nah, this is not really RPC. All right. So now we'll get into why that is, but it's just important to like keep that in mind. And you remember back in episode 1, we mentioned just briefly that there was some debate. I think it was a very brief note, but it was some debate on whether it was or not. So today you'll actually understand why that is. Now, WebSocket, right? So WebSocket certainly also stands out in the sense that it actually does not define the interface model. It has nothing to do with the interface in that sense. Like you can use whatever interface you want. It does not specify that. The same with the encoding. All the WebSocket does is that it's a type of transport. Okay? So when you say, you can say JSON-RPC over WebSocket. You can do that. So in that sense, it's, you have to read that row carefully. So you can't say things like, hey, should I use gRPC or WebSocket? That doesn't make any sense. Right? WebSocket is only a transportation axis, right? A method of transport. It's not like you can't use it in itself. You need to show up with the interface. You need to show up with the encoding, and then WebSocket is the transport. So you could do, JSON-RPC on WebSocket and so on, right? So that's important to. This is a good table to have in your head, right? As you understand these. Great. So let's take a look at a little bit of sort of like background again here, right? So 2 episodes ago, which is episode 1, right? We listed everywhere RPC shows up. REST APIs, right? They're mostly RPC dressed in HTTP, if you will. And we asked the question again, like, is REST really RPC? So that's sort of a battle, if you will, right? But let's just understand what REST is first before we can really understand the issue. So basically, REST comes from Roy Fielding's PhD dissertation from 2000, right? And this was actually the same one we looked at in episode 1. So it's not a protocol; it's an architectural style. It's a set of constraints. So it's not really a protocol, right? But what are the constraints? Well, everything is like, the big constraints are everything is like resources addressed by URLs. Okay, so everything is a noun with an address. So for example, like, /accounts /an address, /blocks /a number, and so on. Okay, so you're operating on these nouns, right? And that's sort of the core. So you have these resources at the core of it. And then you also have a uniform interface in terms of a small fixed set of verbs. So meaning you can get, post, put, delete, etc. There are a few more. And they basically mean the same thing everywhere, right? Get will read something. It reads and never changes anything. Delete removes, right? You don't invent new verbs per endpoint, basically is what it means, right? You don't do something like get balance as a new thing. No, it's like just get, and that's it. You don't invent your own, okay? And then very importantly too is the statelessness of REST. So what that means is that every request, right, it carries everything the server needs. The server doesn't need to remember something. Like I can't make one request, the server then remember something, and then if I later make another request, it combines something. No, everything needs to happen in that one call. It's so in that sense it's stateless. Take all the state I send with you here, do with it what you need to do, and don't remember that I called you. Okay, so when I call you later, it says, I don't know if you called me before, and I don't care. Stateful would be, I remember you called me before, so I need to do something based on you call me before and call me now. That would be stateful. It's not like that. It's stateless. Okay? So there's no per client session between calls, okay? And then the other one that everyone forgets is what's called hypermedia. And this is that responses link to what you can do next. Like web pages link to other pages. So the client can discover the API by following links, not by reading docs. Okay? This is like something I haven't seen anywhere. Nobody's really doing it, but it's actually a very core thing about REST. Just a note. Okay? Now, so here's like we're gonna sort of put both arguments up for why REST should be RPC versus why it should not be RPC. Okay? So here's like a purist argument, if you will. RPC is verbs, not REST. RPC is verbs. Okay? You call actions. So RPC is verbs, REST is nouns. You transfer the state of resources with REST. With RPC, it's verbs, you call actions, okay? Those are the two different. Those are genuinely different mental models, people will say. You think about your resources differently, how you interact with it, and so on. They're very different. In real REST, you never call, for example, get balance. You get, right, with the capital GET, you get a balance resource. That's what you do in REST. You don't call get balance, which is like a verb, like get balance, right? So that's the difference. So you never call transfer, right? You post a new transaction to a collection, for example. You don't call transfer, the verb again, right? So the uniform interface is sort of like the whole point, right? It's like 4 verbs, infinite nouns, and the verbs never change. That's what REST is. Get, post, delete, and so on. I mean, there's more verbs, but you get the point. It's like a fixed set, very small fixed set. Infinite resources you can act on with those verbs, but that's what it is. Okay, so that's just a different way of thinking about, like RPC, right? But by Fielding's own definition, then, right, like REST is basically not RPC by that definition. It's the deliberate opposite, actually. So that's the thing. Now, RPC exposes your function, right? RPC, because you can just call, like, for example, ETH call or ETH get balance or whatever, right? That's exposing your functions. But REST actually hides them behind this uniform set of operations on these resources. You don't really see the underlying functions, if that makes sense, right? So that's not really RPC and HTTP clothes. It's not what it is. It's just a different philosophy of how machines should talk to each other, and that's sort of the point of the purist argument. But Let's now try to make the other side. So if we go look at actual APIs in the wild that call themselves REST, we have things like, I believe we have things like here. Yeah, so let's see. So we did the purest argument REST and not RPC, but let's look at some in the wild, right? We have something like post to API create user, get API get orders, post API send email, post API charges, right? These are some of the actual REST API calls that we see in the wild. Okay, like this one is from Stripe, for example. So these are verbs in the URL, right? Create user, and that's a verb in the URL itself. Okay, create user, get order, send email. There's no hypermedia, there's no link following, there's no uniform interface. It's a function name glued, right, to an HTTP path. That is actually RPC. Okay, so it's it's a call to create user, right? You're not posting to a collection of users, right? You're calling post to this create user with the method name, right, moved right into the URL. Okay, so and then the parameters are moved into the query string in general, like for example here, get orders in the query string, or the body. We can't see the body in this call, but you'll send them along, right? So REST in practice is like hardly anyone implements the hypermedia part. Go look up what that is, by the way. Hypermedia part is actually a very important part of REST, and nobody really seems to know that. But anyway, it certainly doesn't have that in general. And the link following layer is essential, but that is hypermedia, and that's just not there, right? So that's one thing. Now, the overwhelming majority of REST APIs obviously stop short of that, and then what we call this instead is sort of like REST-ish. Okay, so it's not really REST, it's REST-ish. So another way to also say it is actually that these kind of methods here is like basically HTTP RPC. Okay, you could say. So not JSON-RPC, they're kind of HTTP RPC, some people say. So the pragmatist, right? So we covered the purist before, but the pragmatist, we're making that case now. The pragmatist says, call whatever you want, it's RPC. Okay, so that's sort of the friction between the two. We've seen both cases here. So people have sort of converted REST in a certain sense, like sort of converted it into being RPC-esque, right? And that's sort of the issue here, and that's why it's in this gray area, if you will. So anyway, so in reality, it's the spectrum, and the question is really on that interface model axis as we covered before, which is up here, right? So we talked about the interface model layer. So basically, is it nouns, is it verbs, whatever, right? And that's what it comes down to. Now, okay, so what do we got? So, right, so because, okay, so the next thing here is REST also, this is important because REST leans on HTTP's own verbs, okay, so it inherits the HTTP machinery for free. So what that means is get, for example, is safe and cacheable, and that's an important part of REST. So HTTP, you have to understand what I'm saying there is that HTTP has these verbs and has this built-in caching and all that stuff, and REST sort of leans on all that and inherits all that, which is a lot, right? So HTTP has this 30 years of caching, browsers, CDNs, proxies. It's all built around the idea that a get to a URL can be stored and reused. Okay, so a REST, slash block slash a number, can be cached by the entire internet between you and the server because everyone agrees what get means. Okay. Now compare JSON-RPC. Okay, so every JSON-RPC call is a post. To HTTP's caching layer, every post looks potentially states changing. Okay, so none of it caches by default when you do a JSON-RPC call. Okay, so a JSON-RPC call for a block that can never change still sails straight past every cache every time because it's a post with a method buried in the body where no standard cache can see it. Do you see the difference? So a JSON-RPC call just looks like it can't take advantage of HTTP's get, okay, like a REST call can. So even though it is actually just a get, I just need to get something, it doesn't register. Okay, so it doesn't normally get, like, it won't get cached. Okay, So that's actually the resource model, so REST's superpower, right? And you can say that that this is sort of the first crack we're seeing in JSON-RPC, right? That caching RPC is super hard, precisely because RPC threw away HTTP's verbs. Okay, so that's important. So we've named caching as a hard problem before, right? And that's basically why it's hard. Okay, so it comes down to this fundamental structure of that. So we're going to actually look at this in much more depth later in episode 7. So we'll get to that. But of course, in general, when we built these our servers and whatnot, when should we reach for REST, so to speak, the resource model, like over JSON-RPC? Well, I mean, it comes down to like how do you want to design it, but like in general, you want to have your, if your domain really is nouns, rather, right? So if you have users, orders, posts, documents, things like that, and you can create, read, update, delete, and so on, right? Then you want a resource model. Then that's a good one. When you want HTTP caching for free, great, you use it as well. So read heavy APIs, right, over stable data, that's pretty good. You're going to cache a lot, okay? And of course, it's like human debuggable, right? It's pretty easy to debug. So we actually use like REST all the time, right? A lot of stuff uses REST. All right. Now, let's take a look at JSON-RPC that we actually built last time, right? Remember, we built this last time. The JSON-RPC in comparison is, again, an RPC interface model. It has verbs, method, and parameters, right? So it has verbs, methods. So we have this eth get balance, and then parameters that we're sending in. That's how the JSON encoding is just text, right? You can see this whole thing here. This is the JSON encoding. Right? It's text. You can read it easily. You can say, JSON-RPC, what version is it? 2. What's the ID? It's human readable, right? So that's nice. It's also transport agnostic. It doesn't really care what transport layer it sits on. That access we talked about. We ran it last time in episode 2 over HTTP, if you remember. But you can take the exact same envelope here, and you can just run it over WebSocket as well, or whatever else you want. You can do a raw socket. You can do standard in, standard out between 2 local processes, for example, as well. So the transport independence of this format, JSON-RPC, is a real strength of it, right? And we'll get back to that actually, because we're gonna make more notes on that in the WebSocket later. Okay, so does that like make sense? Let's just take a step back. So far we just compared REST. Some people say it's not RPC, right? The purist. Some people say it is RPC, the pragmatist. It's on some scale in between. Okay, fine. Just so you understand it, I'm just covering this in depth so you know if someone brings it up. That's where the industry stands. We covered then JSON-RPC, and I hope you understand the difference between them. We will get to the other methods as well, but that's where we are now. Now, let's then just talk about some good things about JSON-RPC, right? Like what makes it really good. We've covered a few things, but kind of in 3 terms here, you could say it's tiny to adopt JSON-RPC. So there's almost no protocol, right? You just have like this envelope with these 4 fields that we see here, the version number, the ID, the method, the parameters, right? And that's it. You basically built a spec compliant version about 100 lines, right? There's no libraries, no nothing. You just wrote it out like that. So it's very easy, right? It's also human readable, like we just said. You can easily read off what this is. Yep, that's the method we're calling. Yep, that's the parameters, right? Pretty easy. And then it's, again, as we just said, it's universal and it's transport agnostic. So that's really helpful as well, right? So this is exactly why, because of these 3 things, right? It's so sort of like easy to use, easy to implement, and so on. That's exactly why this young, open, multi-language ecosystem, right, would choose it. So that's what helped push blockchain towards choosing it, just so you know. Okay? But of course, every choice on those axes we talked about, right? These axes up here. Every choice we're making has a cost, right? It might be great in one axis and not great in another, and so on, right? So JSON-RPC has 2 big costs, and it's gonna kind of follow us throughout this. Okay. So the first cost. What is the first cost? The first cost is that it's very verbose. So you see here. I mean, it's great that it's verbose for readability. Thank you for putting method, then method name, parameters, and so on, right? But it's very verbose and it's very text-based, right? Which is great for reading it. But you see how every field name is like completely spelled out on every message, right? Numbers travels as strings. In fact, Ethereum sends them as hex strings, right? So that's bytes you pay for, on every call because of this verbosity. And, it's like the machine has to parse that every single time. So you can imagine making like a billion requests, all that you're paying for all that sort of excess, right? That's one real cost, very real cost. And we're going to actually measure that cost. We have some code and we're going to measure that cost, okay? The second cost, if you will, is that it doesn't have any schema. It doesn't have any type safety in terms of the wire. Nothing in the protocol, so to speak, says, yep, this method exists, what parameters it takes and so on, right? And what shape comes back. We saw that in the last episode, right? Because we called some functions that didn't exist, and maybe I forget a character here and so on. It doesn't really check for us. It doesn't really care. It doesn't know. It doesn't have any sense for methods that exist. Does that make sense in what parameters they take? That's what I mean by that. So it doesn't have a schema, right? Yeah. So anyway, so that's what happens. Like the client sort of, as we did last time, we sort of hand rolls the types and then we just hope it'll work, right? We're sending in these parameters and let's hope we parse them correctly and use them correctly, right? That's sort of what happens. So now, those are two of the biggest costs, right, for JSON-RPC. Now, another, I would say, gap that we have, which is JSON-RPC over HTTP, right, is essentially request and response only. So what that means is you ask, you get an answer, and the exchange is over, right? So the server can't push anything to you. So if you're the client here, you ask the server, you get an answer, you send the answer back, okay? That's the client server. The server can't push updates to you, right? And that's what we talked about with, like, your wallet, for example. You might want it to very rapidly push an update to your balance if you send your money somewhere or you swap, because you want to know that it took place and you want to see it, and you don't have to manually click a refresh button, right? So that's where the WebSocket comes in later. We're going to cover that in a little bit later. All right? So that's I hope now you understand, JSON-RPC is great for many things, but it also comes with some costs. Now, so if JSON-RPC is the simplest thing that could possibly work, right, for blockchain, gRPC is sort of the opposite bet to that. So what I mean is, it's the same interface model as we saw earlier, right? Remember that from up here? It's the same interface model here, RPC verbs. However, it changes the other two axes. So it adds this thing called protobuf, which is, it adds the schema like we just talked about. So it actually kind of, it needs to be compiled. It sort of freezes in place. These are the methods, these are the functions, and these are the, method too, and these are the parameters that go with them. It sort of freezes that in place, and this is exactly how to call it, okay? And then it also upgrades to use HTTP2, and we'll cover that in a second too. So anyway, so what is this gRPC thing? So gRPC came out of Google when they open sourced it in 2015. Version 1.0 came out in 2016, and then everything rides on HTTP2. Okay, so the 2015 upgrade to HTTP the HTTP2, is the upgrade to HTTP that lets many calls share one connection at once. So HTTP, is like, again, it asks, it get a response. HTTP2, you can actually have many calls share a single connection because it's much more efficient that way at once. Okay, so it encodes data as well. gRPC does with protocol buffers. This is what we call protobuf, and this is a binary format that Google open sourced all the way back in 2008. So the first thing we write in gRPC is actually not code, it's actually this schema. Okay, so this is what's called the .proto file. And what we're going to see now is this here, this proto file here. And this is, let's say we call that account.proto, for example. So what is this? Well, a request, it has an address, this balance request, it has an address and a block. A reply to that request has a balance. And the balance is a uint64. So it's a real number type, right? It's not a hex string like we're seeing in JSON-RPC, right? It's a real number. And basically there's one method, right? You can call getBalance. And it takes a request, this balance request, and it returns this reply, the balance reply, that are defined up here, right? So this file here, this is the contract, and it is machine readable. So you run a compiler over it, and it generates the client and the server code. You could do that in Go, Python, Java, and so on, a dozen languages, and they're all guaranteed to agree on the exact shapes. So that's the benefit. JSON-RPC, as you remember from a moment ago, had no schema, no type safety on the wire, right? You could misspell a function name, you could, send the wrong parameter, all this kind of stuff. And, it would just crash and you wouldn't really know why. This is basically the answer to that. This won't happen with gRPC. The contract is not in the docs, right? It's in the file that compiles and is enforced on both sides. So that's what happens. So if you misspell a field and it doesn't compile, well, yeah, then you know that you misspelled it. That's the idea. So you won't see any runtime bugs like you can see in JSON-RPC, because you can't misspell anything. It's if it compiles, then you know it'll work. Okay, right. So another thing too, we mentioned like on the wire. When we say on the wire, we basically mean like the information that's shared, right, in this pipe that's between the client and the server. But on the wire for gRPC, the reply is not in text. It's not something like, oh, balance, colon, OX, 1A, 2B, 3, and so on, right? It's like a handful of binary bytes when it comes back, the response in gRPC. So it's not like field names spelled out like up here, right? That we had up here in this thing. It's just bytes. It's just a string of bytes. Okay. So what is the benefit? Well, computers talking bytes. They love bytes. So it's a lot smaller to send. It's a lot faster to parse. All right. And yeah, and what we will actually also dive into is like the byte level layout too. That's how much detail we'll go into. That will be in episode 9. We haven't covered on exactly how those bytes are laid out. We're just saying, at the end of the day, if you took a look at that stream, it wouldn't be like a text like like JSON is, if you will. So what we should know today, and again we'll cover it in a later episode in much more detail, but it's just that there's a trade-off, right? So binary, what do we get? Well, we get size, we get speed, great, but it costs readability. We can't easily read it. A gRPC call in the browser, in the dev tools, it's just bytes. We can't read it. Whereas like for JSON-RPC we can. So, that's the trade-off. Now, in terms of verbose and smaller, we actually have something pretty cool. So what we're going to do now is we're going to run a script that can take a realistic blockchain payload, a block with a few transactions. So this is the kind of stuff that eth_get_block by number returns. So that is like actually a real looking request, and we're going to measure it. So we're going to measure the difference. And so we'll kind of see it like, right now, like what is the difference, right? Okay, so let's actually do that. Okay, so let's bring the code here. So what we're going to do is we're going to run this file here called measure, and this code will be available on GitHub as well. And, I'm going to link to it in the video, in the comment. But what we're going to do is measure the bandwidth, basically, right? Measure the size, right? So we're going to run measure, and it's going to run now, and we'll see the output. Okay, so what's happening here is that same block payload, it has one header and 8 transactions in 3 different ways. That's what we're doing here. So first we're calling like a REST style verbose JSON, and we can see that it's about 6, almost 7 kilobytes here. So one block, right, in general, is like several thousand bytes of JSON, right? And the verbose REST shape is bigger than JSON-RPC, but it's not, as you can see, it's not like that much bigger in the size, because JSON-RPC is relatively compact, and it's 6.1 kilobytes versus 6.8 kilobytes, basically. Right, so it's about 10% or so, and that's could be a little surprising because it's actually like a lot more compact relative to REST, but it doesn't actually matter that much. So the weight of a block is what we're learning here. It's not in the field names, right? It's in the hashes and signatures. That's basically the why this happens. Okay, so field names basically matter less than people assume. Is sort of the learning. Now, you can also see the wire format choice that really moves the needle here is text versus binary, right? Not chatty versus terse JSON. Okay, so the first two don't really change much. One is very verbose JSON, basically. That's like a REST style. It has a lot of stuff, like it's very verbose. And one is compact JSON. Doesn't change so much, about 10%. However, if you switch to binary versus text, and again, we will get to that in episode 9 as to why, it gets a lot more compressed, a lot smaller payload. what we also put here is the gzip numbers as well, and they actually nearly converge. So that's basically the compression, which is eating these repeated field names, basically, right? So whenever you repeat something in a message, you can compress it. It's very compressible. So that's good. And that's why, like, most providers, I think every provider this day, they certainly gzips, right? But as you can see, both these gzips are the same size, right? So it helps, but it doesn't close the gap, right? So gzipping it, sure, 2,500, but binary is still 18, all right? So the other thing we want to look at is parse cost as well. So sure, like how much data you're sending over the wire, that's what we looked at in the top here. But now we're going to look at, well, when you do receive the request, you also need to like parse it, right, and do something with it, right? What function are you calling, what methods, and so on, right? That's what this is now. So this is an average over like 10,000 iterations, and you can see that this verbose JSON again and versus JSON-RPC is very similar, and they're basically about 5-6 microseconds. So that's a lot. Like at 5 million of these calls per minute, if a dApp really makes that many calls, right, per minute, you can see that the JSON-RPC parsing alone takes almost 30 seconds of CPU per minute, right? So that's like 48% of one core doing nothing but turning text into objects. It's figuring out what are you calling, what are you doing with it. That's all it does. So you can see it's like very inefficient, right? That's very important. So okay, so based on this, right, based on these results here that we just ran and kind of understand the size difference between them, like how much bandwidth is moved and how much parsing time it takes, you might ask, like, why don't everybody run gRPC, right? It's smaller, it's faster, and it's type safe. So why isn't just everything gRPC? Easy, we fixed it, right? Well, for that, we need to go back to our two other axes. They basically charge a real price, all right? So what do I mean? Well, it's binary, so no dev tools, readable payloads, you can't do that. So debugging basically means super special tooling to decode these bytes, right? And the thing that makes JSON-RPC lovely at like 2 a.m., which is like you can actually see what's going on, you can see what everything is, right? So you can kind of debug it. gRPC just gives up on, right? So that's a big one. gRPC, as we mentioned, also needs a build step. You need to compile it. So you need a schema, a compiler, the generated code, the version coordination between client and server. It's just friction, which like this 5-line fetch just doesn't have. Okay, so that's another downside of it. And also browsers can't speak it directly. That's an important one. So gRPC needs HTTP/2, right, in a way browsers don't fully expose. So browser clients need a proxy layer in front of it. So for technology, blockchain, whose clients are dApps, right, running in browsers, that's a very serious problem. So all these dApps are running in the browser. gRPC is not really a great fit for that in general, okay, in general. So because it assumes you own both ends, this client and server relationship. So gRPC, it shines when like one team controls the client and the server and can coordinate these schema changes, but it's awkward when the server is public, permissionless endpoint that thousands of strangers' code can call. Does that make sense? So that's why gRPC does not win in general. That's why we're not using that in general, even though it is much more efficient. Okay. So the dominant choice for this sort of like backend service traffic is good for gRPC, right? So backend, you own both client and server, or server 1, server 2. It's great for that. But it's not really a choice you want to make in sort of like an open browser-facing permissionless network, where you don't control the clients, okay? So, which is exactly what blockchain is. So that's where it does not shine. So that basically answers why is gRPC not the predominant, like, RPC method, okay? So I hope that makes sense. Okay, now the final thing we just want to cover in terms of this is basically WebSocket. So it's a very important concept. So the most useful thing to understand about WebSocket is that it's not competing with the others, as we mentioned. It's not JSON-RPC or WebSocket, gRPC or WebSocket like we talked about. It's JSON-RPC, gRPC, and REST are bundles, right? Because we have those three axes. So each of them is technically a bundle, right? They're bundles that mostly differ on the interface model and the encoding between those, right? WebSocket is none of those things. WebSocket is, as we saw, a transport. So we can go back up to our table. It is a transport. It sits down here, right? And you don't choose a WebSocket instead of JSON-RPC. You choose to run JSON-RPC or anything else over WebSocket. So why does it exist, right? And we've touched on this in the episode, of course, but let's cover it in more detail now. So basically, there's a hard limit in plain HTTP that, I'm sure you basically felt before, but like you never named it. So in HTTP, including everything we built in episode 2, by the way, the client always speaks first. So it's like, hey, I have some requests for you, meaning the server. So the client speaks to the server, and the server then responds. So it's like request, response. The server cannot start a connection, and that's important. So the server can say, hey, by the way, the balance was updated. Here's your new balance. It can't say that. The client needs to say, wait, and then ask the server, hey, is my balance updated? The answer might be no. Okay, I'll wait. How long should I wait? I don't know, a few seconds, a few milliseconds, I don't know, right? So if it asks too frequently, that's not good. If it asks too infrequently, well, that's annoying for the user, right? So you see the challenge? It's sort of like pulling information, right? HTTP is. WebSocket is you can push information to. The server can say, the client can say, listen, I'm just going to sit here. I'm not going to ask you. You tell me when you're done. And the server says, great, I'm done. The balance is this. The moment it changes. That's huge. That's great. That's really nice, right? So that's what that transport layer does. Now, that doesn't mean that always that transport layer is the best, of course, but it's just in those situations, it's great to have. Okay? So, right. So, polling, as I alluded to, it basically wastes bandwidth and battery, right? This constant hey, has it changed, has it changed, has it changed. So that's not good. The server should simply be able to push information to the client. And that's exactly what WebSocket does. So the WebSocket starts as a normal HTTP request, okay, and then upgrades the connection into a persistent two-way pipe. So it basically says, hey, I want to open a connection with you, server. And then normally, it'd be like, hey, I have a request. I get a response. Now it says, hey, I want to open a request with you. Server says, great, we can open a request. And then that upgrades into a two-way pipe. So the server can send information back, and the client can send information. And that's the idea of a WebSocket. So that's sort of what happens in a hand-wavy way. It was basically standardized in 2011. And once this connection is open, either side can then send a message at any time. There's no polling. The server pushes the moment something happens. That's the idea. And so the instant a new block lands, the bytes are already on their way to you. And so that's the benefit, right? So when you subscribe, right, to new blocks on Ethereum, you send an ETH subscribe call. And we have that here, ETH subscribe. So you see this here. So when you want to subscribe, you basically tell it, hey, by the way, I'm going to call, using JSON-RPC, I want to start subscribing to new blocks, like the new head of that blockchain, right, of the blockchain. So by sending this payload here, you're basically saying, hey, by the way, I want to start a WebSocket connection with you and tell me when there are new blocks. That's what that means. So the envelope is exactly JSON-RPC as we've seen before. The same thing we built in episode 2. The only thing that now changed is basically the transport underneath. So over plain HTTP, ETH subscribe makes no sense, right? You can't subscribe to anything if it's just plain HTTP, because again, it's like you're asking and getting a response back. So that doesn't make any sense. There's no pipe. There's no open pipe for the node to push these new heads, meaning the new head of the blockchain, back to you, right? So, but over WebSocket, it's natural. So you just subscribe once, and the node start streaming new blocks as long as this connection is live, right? So it's not a different protocol, right? It's the same envelope, same exact envelope. There's no difference between this and like the other thing we did above, but it's just a different pipe, so to speak. It's like it can talk both ways. So that's the idea. So I hope you really get that now. I know we covered in depth, but it's very important to understand. Okay? Now, that is basically machinery. This kind of stuff here is the machinery behind every live thing that you've watched. Again, on MetaMask, you're updating your balance without a refresh. You don't need to click the refresh button. I mean, you can. That's a separate thing. But the WebSocket will make sure to push back to you. At DEX's price, ticking in real time, right? You can see the actual price of something changing in real time. That's a WebSocket connection. Gas price widget, right? That's a WebSocket. You're not asking for the gas price. The widget is live changing the numbers for you. That's a WebSocket. Okay, but it goes beyond blockchain stuff. Like you can see sports scores and all of this stuff, right? All that is like a server that's pushing updates to you. Of course, we can also say this connection, like we're going to have a lot of open connections, right? These can be like liabilities as much as an asset, because it's still a cost to have all these open connections. Does that make sense? Like a normal HTTP is stateless, as we said, right? It just stands alone. You request something, and if that fails, well, you just send it again, right? And then you get a response back. WebSocket is like a very stateful connection, obviously. It's stateful because it's keeping this connection open, and you're sending information back and forth. It has to stay alive, right? So, if the Wi-Fi drops or the connection drops or something like that, well, that kills that pipe that we established. So, in that case, we have to deal with like reconnection and resyncing logic and so on, right? And that could be pretty like fiddly. So there's a lot of like my dApp froze kind of bugs, right? And that's because of that. So that's a downside, right, of WebSockets. There's no free lunch in that sense, right? But the streaming model, you can say, right, it sort of trades the polling waste. Hey, is it updated? Is it updated? Is it updated? For the connection's fragility. You establish a connection, you sort of live with it. Well, if it dies, let's just make sure we reconnect, right? And so it's a trade-off, but it also works very well in general. Excuse me. So, it's a trade-off worth making. But we will look at some of these issues because this fragility is actually very tough to get right. And so in episode 8, we're going to look at synchronization. So what happens when the connection dies? And then in episode 10, we're going to look at resilience as well. Now we're going to answer the question, why did blockchain land on JSON-RPC and what is the cost? So of the 4 models we looked at, right? We list them again here. JSON-RPC, REST, gRPC, and WebSocket. REST is a resource model. You have these resources, like an account and so on. You can act on these resources and whatnot. JSON-RPC, gRPC, and WebSocket, right? Like, why did... So, now we're ready to answer why blockchain landed on JSON-RPC. We have plenty of background now. Right, so we have these different formats: JSON-RPC, REST, which is resource model, right? You have these resources you're acting on, gRPC, and WebSocket. So was it the right call to choose JSON-RPC? That's the answer. The short answer is yes, it was the right answer. Probably not surprising, but it still has cost, and it still has cost us, right? So making that decision is not only yes, and it was just perfect, right? Because we have those 3 axes, and we have all the costs we talked about. Both things can be true at the same time. It was the right decision, but it also cost us. So, Ethereum launched in 2015, right? Let's go back. You can sort of picture the constraints that the people designing the interface actually faced at the time, right? You got to sort of like run this 3-axis menu against them. The clients are in browsers. The dApps are wallets run as JavaScript in a web page, right? JSON is native to JavaScript and the browser. gRPC, remember, can't run in a browser without a proxy, so that's sort of like strike 1 against gRPC. Does that make sense? That's one thing. Also, anyone can write a client in any language, in blockchain, right? It's a permissionless network. The whole point is that you don't need anyone's blessing to build on it. So the interface had to be the lowest common denominator every language already speaks, which is JSON on HTTP. No compiler, no schema tool chain, no build step, right? So that's strike 2 against gRPC. Anyone can run a node too. Multiple independent teams write the node software. Geth, what was parity, others. So like a protocol that's just a readable JSON envelope over HTTP is something a dozen teams can each implement from pros spec, right? We saw that spec, I think in last episode we took a look at it, and basically stay compatible, right? A heavy schema and code gen system, which is what gRPC is just, far more, it's just far more to coordinate rather, right? Over this decentralization. So not a good fit for that. And also like the interface model genuinely is verbs, right? So REST's resource model, blockchain operations are actually actions like get balance, call, send raw transaction, estimate gas. They're function calls, okay? So they're not what's called CRUD, like look that up for REST on nouns, right? So, that's a concept associated with the REST, but they're actually these function calls. So the RPC model just fits better in this domain. So the resource model would have had to constantly fight against the grain, so to speak, right? And readability and openness are values as well, right, in the blockchain ecosystem. So JSON-RPC fits well there as well. So if you sort of add up all these things, this browser native, language agnostic, zero tool chain, verb shaped, human readable interface is JSON-RPC, and it's kind of like the answer. It's not only an acceptable answer, it was, it's really the right call to make. But again, every one of those strengths was tuned for bootstrapping an ecosystem in 2015. Our protocol and things like that is that once the world built on it, right, you're kind of stuck with it. That's just the fact. So the thing is, the scale at the time that they launched in 2015 has changed a lot from today, right? So you can kind of say that. So things have changed a lot from 2015 to today, of course. So it was a great choice at the time. Still is a great choice, but today at the scale today, I guess is the point. Is there's a lot of room for optimizing that, right? So verbosity we touched on. It leads to bandwidth issues, right? Thousands of bytes per block, hex string for every number. Every byte is billed by the provider, right? So you're paying for all that. Leading to parse cost, right? Every response parsed from text millions of times a minute. Every provider indexer, right? So you're just, that's real CPU power. We saw the measurement. We ran the code. That's rough as well, right? And there's no schema, so there's no safety. There's no code gen and so on. So eth_star, meaning any like eth call, it lives in prose. It doesn't live meaning it's just you just write it out, and if you mistype it, that's an issue. But gRPC would be perfect for that, right? And also there's like no native streaming, so live data needs WebSocket, of course, stabled alongside the HTTP path. So that's the second stateful drop prone channel, right, that we're creating. So there's a lot of trade-offs in all of these issues, by the way. They were basically invisible in 2015 when it was first created, with a few thousand users, a handful of dApps, right? But the whole point of the series 2 is to say, like, the world has changed. The blockchain world has changed, and it's changing every day. Now we have billions of calls a day. We're not back in 2015 when we made these decisions. So dApps can fire dozens of calls per screen, right? And we saw that last time, actually. So per screen, you can really make a lot of calls, and you have to make a lot of calls. Users on phones, right? Providers charging by the request. You can imagine what happens, right? Those are the invisible trade-offs that are very visible now and very expensive. It's a very expensive tax. You're paying for it as a dApp project for all this unnecessary overhead, if you will. So let's consider now this new world, right? It's enormous. We have more and more people use blockchain technology. All these dApp need to call it. So that's sort of like the idea of the remainder of this series, to sort of kind of say, like, all right, let's look at RPC technology. Where, like, how far have we come with it, since 2015, and like, where should we go with it? And we're going to see that not a lot has actually happened. Not a lot. Some things have happened. We're going to cover that in this series, but not a lot at a fundamental level, and we're going to touch more on that at the end. But we're going to touch on caching as well, and we're going to touch more on caching in episode 7. We're going to keep state in sync without pulling the fragile connection, as we talked about. That's episode 8. We're going to get the bytes down and parse the cost, and we're going to eliminate that. That's episode 9. And we're going to survive when an endpoint drops. That's episode 10. And we're going to beating the distance to the user entirely in episode 11. So all these things in the future we're going to build up and improve and improve and improve to modern day. But we're also going to see, compared to 2015, still we haven't changed the RPC technology at a fundamental level. That's going to come much later. Okay, so let's again take our original call here. This is what we opened the whole series with, right? Remember that? We thought it was going to be just an easy call, right? Client.get balance. What could be complex behind it? Well, we're starting to see there's actually a lot going on in this line, right? First of all, there's a lot of many ways to make this call. At the beginning of this, episode, you might have been like, well, I don't know which they are. I don't really know, much about these things. But now you do. We have JSON-RPC. It's RPC verbs. Remember, it's JSON text we're sending. It's transport agnostic, right? We can send it over HTTP, over WebSocket, whatever. We also talked about REST. That's another method we can use to send this. That was the resource model, right? And that leans on the HTTP's verbs. That's a benefit, right? And the HTTP's caching, by extension. right? So that was good. That's another way we can do it. And then gRPC, as we learned, that's the opposite bet, so to speak, right? It's binary, it's schema first, it's fast, and if you own both the ends, the client and the server, you can do it. And then, of course, at the end, there's the WebSocket one, which is, as we know now, it's not a rival to the others. It's a transport layer, right? So it's just a different way to do the pipe between the client and the server. You know now about the 3 axes, the interface model, the encoding that we do to the data that we send, and the transport, how we're transporting it. Okay? Every protocol is a bundle of those 3 choices. That's why we call it a bundle, because you have to choose these 3, so that's what you have to have in mind. And sort of that's the whole landscape. So this line again, right? This is the series signature, right? So when you call getBalance, under the hood, it is JSON-RPC. We saw that last time. We built that last time in episode 2. Over HTTP as a post call. Okay, we know that from last time, and we know now why that is. Why is it that? Why is it not gRPC? If someone said, why don't you use gRPC? You should now understand why. Why is it not REST? You understand that now as well, right? And, and why is it not WebSocket? Well, depends. I mean, you could do it over WebSocket, but that depends on how the client interface, implements how you do that. But you get the point. So that's important. That was the goal of this episode, right? Is to make you understand. Like last time we actually built it, but why did we build it? Why did we not build in the last episode gRPC? Why did we not build other things? Well, JSON-RPC is the method that's used in blockchain. You know now why. Okay? Now, in the next episode, now we're going to go inside the choice we just examined, and we're going to also get to the real ETH _star, meaning, ETH, different methods, right? Namespace. We're going to get into that, and we're going to see how blockchains actually expose themselves to the world, so to speak. Reading versus writing. What ETH call really does. We're going to see that, and we're going to see the strange shape of all of this, okay? So we have picked our protocol, JSON-RPC, and next we're going to see sort of like what lives inside of it, so to speak. Like, what does this getBalance do? How do we talk to the blockchain, things like that? How does it communicate to us? So I hope episode 1, we learned history. Episode 2, we actually built our first JSON-RPC server, nothing but blockchain. Now we know why we built it with that protocol. We have no question about it. Why not gRPC? Why not other method? Doesn't matter. We know why JSON-RPC. We know why. So we feel very comfortable about why we did what we did in episode 2 now, right? We know it. And then episode 4, let's finally dive in to get some blockchain. How can we read and write? So I'm super excited about that. Thank you, as always, for following along.